Hello and welcome again to another series of lectures in functional analysis. So here we would like to provide an application of the Lax-Milgram lemma that we have discussed in the previous lecture. So first, let us recall the Lax-Milgram lemma. So suppose we have a Hilbert space X and a bilinear bounded and coercive form A defined on this Hilbert space. Then, given f in the dual space of X, one can find a unique solution X in the Hilbert space that satisfies this variational problem that is highlighted here. And moreover, uh, this solution is stable with respect to the given data f in the dual space. So as an example of an application of this Lax-Milgram lemma, we consider an elliptic boundary value problem, namely a stationary heat source problem. So here, our goal is to determine a function u defined on some set omega, taking values in R, satisfying the following partial differential equation. So here we have the negative divergence of some matrix valued function A times the gradient of u plus some function C times the unknown function u equal to some h of x for x in omega. And let's say we have the following conormal derivative, and this is 0 when, let's say, x is on the boundary of omega. So the second term here is what we call the conormal derivative, and nu is the normal vector outward of the boundary, or outward to the boundary. So suppose this is our domain omega. You have a point x on the boundary. Then nu of x would be this vector, unit vector outward to omega. Okay. And you can think of h here as the heat source, and u as the temperature distribution. This matrix A here can be thought as your conductivity matrix. Or this is diffusion matrix, which is responsible how fast or how slow the heat propagates. And see here, you can think of this as some sort of a friction term. So we want to determine a function that given a heat source, knowing the diffusion matrix and the let's say the function C, a function u that satisfies this boundary value problem, which we denote by BVP. Of course, before we proceed, we need to provide conditions for the given data here. So we suppose that omega is an open, bounded, and connected domain with a sufficiently smooth boundary. Okay, by this, loosely speaking, you can think of the boundary of your domain to be parameterized by a piecewise parameterized by, let's say, smooth functions. So we will not go into the details of this technical concept, but just think of, for example, a domain in R2 when n is equal to 2, where your boundary can be, after some, let's say, rotation, this graph here is, let's say, is smooth enough. Let's say a C2, that is continuously twice differentiable. And likewise, we have the following given data. So we suppose that the coefficient C is essentially bounded, and the heat source is square integrable, and A is a matrix valued function whose components are essentially bounded. And suppose that A is coercive, or what we call elliptic. And by this, we mean that A of x times a vector in Rn, taking the dot product with xi, is greater than some constant alpha times the Euclidean norm of xi squared. For almost every x in omega. So there exists an alpha positive that satisfies this inequality. And suppose also that C is bounded from below. Let's say this is bounded below by some constant gamma, which is also positive for almost every x in the domain omega. And these are our assumptions on the data H. C and then A. Now, suppose I have a solution that satisfies this boundary value problem. So supposedly U is continuously twice differentiable up to the boundary. And suppose that this satisfies the boundary value problem. Okay. Now, given, let's say, a phi, which is also C2, this is what we call a test function. What we do is we multiply the first equation, that is the differential equation, by phi, and then integrate both sides. And from this, we obtain the following equation. So this process is similar to our motivation in the definition of weak derivatives. Okay, so for the first term, we apply the divergence theorem. So using the divergence theorem in vector calculus, you will get the first term is equal to negative of the boundary integral of aux dot mu x times phi of x dx plus another term, which is aux gradient aux. So there's a missing gradient here. So let us correct that one. And there's also a missing gradient here. Nu of x phi of x dx. Okay. Then this is the gradient phi of x dx. Okay, so those who are not familiar with vector calculus, recall that the divergence or the gradient of a function u is namely the vector consisting of the derivatives. So that's, let's say, dx1 u up to dxn u. And here, the divergence of a vector field is just the sum of the derivatives. So the ith derivative of the ith component of your vector field I from 1 to n. So use the divergence theorem in order to rewrite the first term in the following way. Okay, we know that this will vanish according to the boundary condition. That's the second equation here. The conormal derivative is 0, therefore the integral here is 0. The boundary integral, more precisely, will vanish. So substituting this in the above equation, we get the following equation. So thus, here we have the term obtained from applying the divergence theorem. And here is the another corresponding bilinear term. And then the right-hand side. Okay. And from this will motivate us the definition of, or this is a motivation for the definition of what we call weak solutions of our boundary value problem. So a function u in H1, okay? Take note that here we only need that u and a gradient of u exist, okay? And later we will see that these integrals are well defined due to the assumption on the matrix function A and the scalar function C, that these are indeed well defined. Okay. So this H1 function, the Sobolev H1 function, which is, by the way, W12. So we know that this is a Hilbert space. This is called a weak solution of our boundary value problem if this variational problem is valid for all test function phi that is also in H1. So here, and likewise, we say that a function u, which is C2 omega bar, is called a strong solution of our boundary value problem if the equations are satisfied for almost every x in omega and x on the boundary. In other words, these two equations here are satisfied for almost every x in the domain and x on the boundary. So according to our discussion, a weak solution or a strong solution is necessarily a weak solution. So this is what we have established in fact. So starting from a strong solution U in C2, we showed that this variational problem here is satisfied. Therefore, we have a weak solution to our boundary value problem. So here, we cannot, however, go the other way around. In other words, if you have a weak solution, then you cannot go in the reverse direction because we do not know if this divergence exists, because we only know that U is only weakly differentiable. However, if U is a weak solution and it is smooth, in other words, it's a C2 bar, then it is also a strong solution. So this implication can be stated alternatively as follows. So if you have a weak solution and it is regular enough in this sense that it is C2, then it is also a strong solution. Since, okay, now that you have this variational problem, you can go backwards and apply, let's say, the fundamental lemma of the calculus of variations to observe that the weak solution having this regularity is also a strong solution. Okay, so here is an alternative way of solving the boundary value problem. First, if you want to establish the existence of a solution, you first show that it has a weak solution, and then it is regular enough. In other words, it is continuously twice differentiable up to the boundary. So this is a very wide field in partial differential equations, but just to give you an idea, let us establish the existence of weak solutions. So here we will show the following. In fact, the weak solution is unique. So to prove this claim, we will apply the Lax-Milgram lemma. So going back to the statement of the Lax-Milgram lemma, we need to write this in terms of a bilinear form and an element of the dual space. So here, our Hilbert space is the Sobolev space H1. So first, let us recall that H1 omega is a Hilbert space with respect to the inner product the inner product would be the following: H1. Okay, so here we will not emphasize the domain in writing the inner products for simplicity. So this is the same as the L2 inner product, and then we do not explicitly write the argument of or the variable of integration plus the gradient of u dot the gradient of b dx. So now let us define the following forms. So A from H1 cross H1, and let's say F from H1 to R as follows. So these are basically the left-hand side and the right-hand side of this variational problem. So this is the integral of A, and again, ignoring the argument x in the integration, we have this sum x, and f phi is the right-hand side dx. So this is for all phi and u in H1 omega. Having this forms, then our variational problem is equivalent to the following. So we would like to find a u in H1 omega such that AU of phi is equal to f of phi for every phi in H1 omega. So we have written the variational problem in the framework of the Lax-Milgram lemma. So to establish the existence and uniqueness of this problem, therefore, it is enough to prove that A and F satisfy the conditions for the in the Lax-Milgram lemma. First, take note that A and F, or A is bilinear, and F is linear. Well, you can prove this easily from the linearity of the Lebesgue integral. Next, let us show that F is bounded. And in particular, this implies that F must be in the dual space of H1. So to show a boundedness, let us estimate the value So for all test function phi, h1 omega, this is, okay, applying the definition of f. This is the integral of h times phi. And then here, you now apply your Cauchy-Schwarz inequality to say that this is less than the product of L2, less than or equal to the product of the L2 norms. And since the L2 norm is bounded above by the H1 norm, okay. Take note that for the H1 norm, you also include the L2 norm of the gradient. Okay, since here again, the H1 norm squared is the same as the L2 norm squared plus the L2 norm of your gradient. So this implies that, of course, f is bounded. Hence, from this inequality, we can also see that the dual norm is less than or equal to the L2 norm. So for consistency, let us put the domain in the L2 space and also in the H1 space. Okay. So here, let us put the domain for emphasis. So that's the boundedness of the linear form f. In a similar manner, we can show that A is bounded. So for all u and phi in H1 omega, you have the following. So let us estimate the magnitude of the bilinear form A evaluated at these two arguments. So this is okay. Since we are in the real case, it is enough to consider or I should say applying the definition of your bilinear form. And then here you now apply a Holder's inequality. So you have L infinity norm of A times the L2 norm of U, the gradient of U times the L2 norm of the gradient of phi. And similarly, for the second term, you have the L infinity norm of C times the L2 norm of U times the L2 norm of phi. And this implies that, okay, taking the max between the L infinity norms of the coefficient matrix and the scalar matrix C. And then I take note that each of these is bounded above by the H1 norm. So we have here times the H1 norm of U and then the H1 norm of phi. And this proves the boundedness of your bilinear form A. And finally, for coercivity, so for all U in H1 omega, if we compute the bilinear form evaluated at this function U, again using the definition, this is A gradient of U, gradient of U plus C of U squared dx. And take note that applying the ellipticity of A, the first integral is bounded from below by alpha times the norm of gradient U squared. So we pull out the smallest between the two. So this is now, let's say, and take note that C is bounded from below by gamma. Okay. And taking the minimum between alpha and gamma, we end up with this term. And of course, this integral term is nothing but the H1 norm of U squared. And due to our assumption, alpha and gamma are positive, so this is also positive. So all of the conditions of the Lax-Milgram lemma are satisfied. That is, A is bilinear and F is linear. F is bounded, A is bounded, and A is coercive. So therefore, by Lax-Milgram lemma, there exists a unique U in H1 omega such that AU phi is equal to F of phi for any test function phi in H1 omega. And this is a weak solution of our problem according to this equivalence that we have stated a while ago. Moreover, we have stability. So going back to the statement of the Lax-Milgram lemma, you can see that the H1 norm of your weak solution is less than or equal to the bound for A, that is the largest between the L infinity norm of the coefficient matrix and the L infinity norm of the scalar matrix, scalar function C. And let us write that as a constant C. Divided by the coercivity constant, which is the minimum between alpha and gamma. This is less than the dual norm of F, but we know that the dual norm is less than the L2 norm of the heat source. So we have established the existence and uniqueness of the weak solution of our boundary value problem. And we have also the stability of the solution. Okay, so small changes in the heat source with respect to the L2 norm leads to small changes in the weak solution with respect to the H1 norm. So this concept of a weak solution might be superficial at this point, but finding let's say a solution of a strong solution of your boundary problem, this would be a first step. So this will serve as a first step in finding strong solutions. So the proof of regularity is a bit involved. So for those who are interested, you may, for instance, look at the standard books in partial differential equations. For instance, the book of Evans. Okay, so nevertheless, this concept of weak solution serves as what? A foundation in approximating solutions for our boundary value problem. And the main idea is, in fact, using the concept of finite elements to discretize this boundary value problem or this variational problem into a finite dimensional space. So one has to look for appropriate finite dimensional subspaces of H1 and consider, let's say, the problem on this finite dimensional setting. The idea is that based on this finite dimensional setup, you can, of course, present or discuss an appropriate basis of your finite dimensional vector space. Once you have presented the basis, you can now write this variational problem in the finite dimensional setting as a matrix equation. So this idea of weak solutions is very useful in the numerical approximations of or in the numerical approximations for this type of problems. So that's it for the Lax-Milgram lemma and its application for elliptic boundary value problems. So in the next lecture, we will discuss theorems that go beyond the classical Lax-Milgram lemma.